Okay, well, I think we should get started. People are still coming in. Okay, so let's get started with the second part of the day. Hello, everyone. It's my pleasure to introduce Professor Bing Liu. Bing Liu is a distinguished professor at the University of Illinois, Chicago. He received his PhD in AA from University of Edinburgh. His current research interest includes continual lifelong learning dialogue systems, sentiment analysis, machine learning, and NLP. I think if you work in NLP, you would already know Bing. He has published extensively in several conferences and journals, and he has also authored 4 books. One is actually about lifelong machine learning, and it's probably the only book on lifelong machine learning right now. 2 about sentiment analysis and 1 about web mining. So Bing is also like a fellow of ACM AAA and IEEE. So thank you for accepting our invitation, Bing.
Can you hear me? Okay. Thanks for the introduction, and also thanks for the invitation. So today I'm going to talk about something to try to connect all these guys together: continual learning, auto distribution detection, and also the open world learning, which becomes quite important when we come to study the embodied systems and also the agents. So human beings are really our human brain are really hardwired to learn continuously and all the time. We are very curious creatures, and anything we see which is unexpected, we want to learn about it. And for example, if you put a box in the middle of the room, sooner or later you're going to open it, right? You're not going to leave it that close. So we are very, very interesting creatures, and we are always thinking about learning. Okay. So how do we make machine do sort of similar things? Do the similar things, so they can face the real world and go to sort of deal with unexpected situations, and of course at the same time, and they can communicate with humans, with other agents, and also have some kind of interaction with the environment. Okay, so everything has to be done sort of self-initiation, self-motivated, instead of guided or sort of controlled by human engineers. So the classic machine learning paradigm is something like this kind of a waterfall kind of situation. You have a task, you have a data set, and then you got a machine learning algorithm that produce a model, and that model goes to application. Okay, goes to application. There are lots of weaknesses about this particular paradigm. And for example, the first one is the closed world assumption. So we are expecting nothing new. So everything we have learned so far, we also expect to see only those things. Okay, so putting another way, is that everything we see in testing must have been seen in training. Okay? But in real world, that's not the situation. Okay, if you send a robot out, and you will see everything is different. Okay? Everything is different from what you have learned. And also, there's no knowledge accumulation. We got a piece of data and just learn from that, and then we have another task we learn separately, and there's no connection between them. Okay, no connection. And also, there's no learning after deployment. So there's human beings always learning. Okay, it's always learning. And never mind whether you got a training or not training. You probably got formal training in schools or whatever schools you have. But after you go to work, you continue to learn. You continue to learn. All right. And so what do we mean by closed world? What do we mean by open world? Which is pretty simple. And closed world just basically says whatever the classes you have in testing should be a subset of training. It should be a subset of training. And in the open world, we say the test has something different, and we have never seen it before. Okay, I've never seen it before. No. So if we are learning in this kind of scenario, or this sort of more practical dynamic scenario, and we are doing open world continual learning. Yeah, because open world is always a continual learning process. You can't say, I see something, I learn, that's it, stop. I mean, you have to keep going. Okay, keep going. Okay, so I just sort of try to save this word of continuum. And also for a system, if you cannot detect, if you have any automatic system, or autonomous systems, if you cannot detect anything new, there's no way you can learn. Okay, there's no way you can learn. Okay, because it's always the same. You see, which is unexpected, which basically motivate you to learn the new thing, So then we have this particular sort of framework. It's not exactly a formal model, but a framework. How do we make the system autonomous? Okay, make the system autonomous. So this is basically the work we supported by DARPA, and it was probably 100 people. I know it's all kind of discussions. Somehow we, I probably want to be careful, but I think we sort of converge to an idea. So what this autonomous system should be. Okay, should be. I'm going to talk about this later. So let's start with the continual learning or lifelong learning, which we called earlier. So continual learning, essentially, most of people here are familiar with continual learning. For those people who are not in this area, and for the benefit of those people, and let's just give a brief introduction. So we are learning a sequence of tasks. Okay, we're learning a sequence of tasks, and each task have some training data. And most of the time we do continue supervised learning, but of course we can do a lot of unsupervised learning as well, especially when you have this language model, when you want to do pre-training and you want to do this continual unsupervised, or sometimes we call it self-supervised. So the two goals, without catastrophic forgetting. So we don't want system to learn the new task and forget the old task. Okay, forget old task. And of course, we also want knowledge transfer. So this was the main objective for sort of continual learning or lifelong learning before 2015 or something like that. And people have been focusing mostly on knowledge transfer, because and this time we talk about the task that are very, very similar, very similar. So if we put this pictorially, something like this, later I'm going to use this one to expand this into a more open world situation, which gets very complicated. Okay, so we have a sequence of tasks, and this is the current task or the new task we're learning, and then we have the data set, and then we go to this continual learner, and assume we have knowledge base, so now knowledge goes here, and then basically pick up the knowledge which are sort of suitable for this particular task, new task, and then we can use that knowledge to help us to learn better. Okay, so here we put this explicitly, the knowledge base and also the task-based knowledge miner, but in real situation when we deal with neural nets, we probably don't really have an explicit knowledge base, because the whole network will be the knowledge base. So the past research was still sort of to produce a model that goes to application, all right? And so there's some assumptions. So the first assumption is after the task is learned, the data is no longer accessible, okay? At least most of it, okay? We do have this replay techniques, so we can save a little bit of data from the past, but that does not help completely. Okay, does not help completely. It helps a little bit, but it does not help completely. So we still can make the assumption we do not save data in the past. So this is something similar to the human beings. Probably, in the past, we have seen so much stuff. Every time we see a new thing, and we obviously don't go to retrain the whole model, right? It's just impossible. The whole, we have seen so much in the past, and we just use this particular sort of, for example, object, a new animal. We just learn this animal, and that's it. We don't really have to go back, to compare the similarity with everybody, and that's just impossible to do. Another one is both the new task and the training data, at least at this moment, are given by the engineers or given by the user. So they're not discovered by the system itself. Okay, it's not discovered itself. If we want the system to be autonomous and to face the real world, and we need to sort of get rid of this assumption. So system has to get the data and get the task. So basically discover a new task and also to get the training data by itself as well. Okay. So we have two popular continual learning settings. The first one is called a task incremental learning. And in that case, essentially we're trying to build a separate model for each task. So they do not have to be sort of interacting with each other. Okay, completely separate. So this was the case before 2015. There's most of the research on continual learning basically dealing with the task-oriented continual learning. Okay, task-oriented continual learning. So for example, the task one, it could be just learning to recognize different breeds of dogs. And the second task could be just recognize different animals. And the third one will be different type of fish. So you can see there are intersections among these tasks. For example, the animals, definitely include dogs and also include fish. So we're building complete separate models. If we want to define this mathematically, and then we just have to remember this part. So we have the input X, and we also have the task ID, kind of the task ID, and they give us the classes. Okay, give us the classes. So this is in training and in testing, and we need the T. Okay, we need the T because in this particular situation, for example, I'll give you a dog. I mean, how are you going to classify it? Is it an animal or is it just a particular breed of dog? Okay, so you need the task ID. Task ID. But a more difficult case or more difficult scenario is this sort of class incremental learning. And in this case, we're producing only a single model, and we want this model to deal with any sort of test instances. Okay, For example, this is the task one. Let's say today we see pig and the cat, and we just learn pig and the cat. Tomorrow we see sheep, and we learn sheep. And the day after tomorrow, we'll probably see chicken and dogs. And then after that, we'll see the horse and the cows, all the things. And then we just basically learn them. And at the test time, I'll just give you an image. I don't tell you, which day you saw this thing, and you just basically tell me what animal it is. Okay, what animal it is. All right. So you can see in the definition, and we do not have the T anymore. Okay, we do not have the task ID anymore. So this is the situation, very much sort of like what we do, sort of in everyday life. We see new things, we keep learning the new things, and accumulating the knowledge. So later I'm going to put all this together into the same kind of framework. Okay, same kind of framework. All right. So this problem is difficult. Okay, and we talk about this catastrophic forgetting because when we learn a new model, learn a new task, and the networks are really fixed for the previous task. So if you want to learn this new thing, obviously you have to tickle somewhere, right? You have to change something to make sure this guy will work. If you want to make this guy to work, and then obviously when you change something, you're going to disrupt what you have learned in the past, some kind of knowledge is got forgotten. However, this class incremental learning has a major difficulty, which is not exactly forgetting. It's the thing like what we call the inter-task class separation. Because you have learned something in the past, and now you are learning something new, and you don't have the data for the past. So how do you establish decision boundary between the current task and anything you learned in the past? There's no way you can do it because you don't see what happens in the past. Okay, so this is called inter-task class separation. So this is more difficult to deal with. So even you have replay data, it helps a little bit, but still you don't solve this problem. Okay, don't solve this problem. So we have been thinking about this problem for a while, and we're also trying to think about this problem sort of independent of any models you use, so regardless what our classification algorithm you use. So by nature, how this problem can be solved. Okay, so I think we humans do this type of thing. We look at this thing, and we somehow can figure out that this is not something we have learned in the past. So we are pretty good at that. Okay, pretty good at that. Okay. So then let's see some mathematics. Okay, mathematics. So for this particular problem, and I just want to mention, let's just mention interesting assumption. Assumption is realistic. It's not something which is unrealistic assumption. We say we learn this pig and cat and sheep and those things. These classes, all these classes, they have no intersection. Okay, they are all completely independent. They're sort of disjoint. Okay, that's only assumption we're making. Okay, only assumption we're making. Okay, if we make that assumption, sorry. If we make that assumption, then this will hold. Okay, so we're trying to decompose this particular problem into two sub-problems, basically two probabilities. The first one is within task prediction probability, and task ID prediction probability. This sounds pretty obvious. Okay, sounds pretty obvious. So mathematically, we just write this way. We say X belongs to the domain of this particular thing, which is the task K. This 0 means a particular task. Okay. 0 means a particular task. J means a particular class within that task. Okay, within that task. All right. So X belongs to a particular distribution, and within that distribution, that particular task and the particular class. Okay. So that can be written as the product of these two guys. The first thing, you have the prediction probability of X belongs to a particular task. Okay, that multiplied by given the task, K's task, what is the probability of X belong to a particular class, So this applies to, if your task can have many classes or just a single class, it doesn't really matter. Okay, it doesn't really matter. It applies to anything, and also applies to sort of online kind of situation. Data streams comes in. This is all fine. Okay, this is all fine. So what is interesting theoretical result here is the good This is WP. WP of course means within task. Basically, we say given the condition, the task is fixed. Okay, task is fixed. So this is WP. This is the TP. And so the result is that WP and TP, don't worry about OD yet, are necessary, sufficient conditions for good CIL. Okay, if you look at this thing, obviously it's true. Okay, obviously it's true if you think this equation itself makes sense. But the major thing here is that prediction of TP, the task prediction, is correlated with out of distribution detection, right? And this is the major thing. This is the major thing because this gets a continual learning out of distribution detection, and this sort of open world learning completely got connected. So in terms of proof, we just use the cross entropy type of thing to prove. But if you don't really need to prove, because this formula actually tells you that. So you can prove this is bounded by these two guys, and also important thing is the TP and the OOD detection bound each other. Okay, bound each other. Okay. You can basically say use a TP and a TP. This is basically the same thing. This is true in the sense, if you think about it, right? When we try to predict this thing, if your out of distribution is no good, then your prediction is not going to be good. Okay, it's not going to be good. All right. And then if we have this condition, we'll have this thing proving, and then we obviously can show and the loss of this guy is bounded by WP and OOD detection. Okay, OOD detection. So these three theorems just say, okay, this is sufficient. Okay, sufficient. If we got this two good, so WP, TP, or OOD is sufficient to guarantee good CIL. However, that's not enough. We want to say this is also necessary. Okay, this is all necessary. Okay, necessary. Essentially, we want to show that guy is necessary. And it turns out this, of course, is also applicable if we do unsupervised continual learning. So, for example, sorry. When you do unsupervised continual learning, for example, you have a large language model, you continue pre-train with particular domain data, and then you go to pre-train on another domain data, that kind of thing. And then when you come to the application, you need to spot which domain your task is about. So in that case, you still need OOD detection, right? You still saying for each task, you need to identify everything belongs to this guy or not belongs to this guy. Okay, basically you have to do that. So this is sort of applicable to the situation of unsupervised or self-supervised. So what is the intuition? So intuition is actually quite simple. Okay, because as we said, we want to separate the new classes with the past. Actually, we also need to consider the future, right? Because for continual learning, you can't just say like isolate learning, I'm just looking at this task. You have to look at the past, and you also have to anticipate the future. So what is the technique can do that? OOD detection. There's nothing else. Because you don't see the data in the past, you don't see the data in the future at this moment. So if you can do good OOD detection, then that doesn't really matter anymore. the problem is solved. Okay, problem is solved. Of course, in this case, if the problem is solved, if the OD is solved, then everything just reduced to the WP within task kind of situation, within task prediction. Okay. So obviously, this theory just basically this theory just say what the CIL system should achieve, but it does not say how to achieve it. Okay? It does not say how to achieve it. All right. So we do have, of course, some. Well, I'll show you algorithm shortly. So an interesting thing. Sorry. So this can be a little bit controversial. Sorry. Since we need to consider the past and the future, okay, and then what is the implication of that regarding representation learning? Okay, and are those traditional principles and theories about machine learning still appropriate or not? Okay, so here I give an example with Occam's razor. All right, Occam's razor, obviously, with everybody knows if you do machine learning, you want to basically prefer the simplest model, which give you sort of competitive results. But what do you mean by simplest model? Okay, simplest model. Okay, if you think about in terms of cross entropy, let's say we're going to classify these two guys. Simplest features. Cross entropy basically give you simple features. Right? Color is good enough, right? One is black, one is red. That's it. We don't need to worry anything about or anything else. However, later on, in the future, the crow comes in. We have to recognize crow, and then you have a problem because the crow is black too. And then you see, how can we solve this problem? So in terms of learning feature representation, and we probably have to do something different. So last year, SML, we talked about this holistic representation. So pretty much you have to learn everything. You try to learn everything. So all the characteristics of this object, for example, apple is the shape and everything, and the cow, the shape, everything is not just black and white, black and the red. Okay. So in that case, and then we can sort of say, when something comes in the future or something in the past, we are okay. We are okay. So I believe human beings probably doing something like that, right? We are not saying, oh, this is black or this is white. That's it. I mean, we obviously sort of recognize all the characteristics of that object. Okay, and otherwise we'll have a problem because in the future, anything we see, if we do not have full representation of that objects we have seen in the past, then in the future, we're going to miss a lot of stuff we need to learn. So here we just basically propose an algorithm which does that, essentially say, we have to deal with forgetting still. We have to deal with forgetting. So in this case, we deal with forgetting using a task-oriented continual learning algorithm. Okay, we talk about those two types of continual learning, right? The first one is task incremental, another one is class incremental. So the task incremental problem is pretty much solved. There's no, because we're building separate models, but of course the model is still in the same neural net, okay, the same neural nets. And there are many algorithms which can deal with TIL without forgetting, okay, without forgetting. So if this is the case, so we can just basically use TIL for each model. For each model, each task has a separate model. For each model, instead of building a traditional cross-entropy classifier, we built an out-of-distribution model. Can build an out-of-distribution model. That's it. Okay, that's it. All right. So in this case, we have, this is HAT, this is one of those TIL algorithm, and which is pretty much no forgetting at all, and then plus out-of-distribution algorithm. Okay, instead of using the cross entropy to directly build a model for each particular task, we just basically switch that with auto-distribution detection model. Okay, so normally auto-distribution detection can identify auto-distribution stuff and also can classify within task, right, in distribution classes as well. performs both tasks. So the second method, we use the pre-trained model and also leverage some replay data. And in this case, of course, we do a lot better because you have some pre-trained models. So in this case, you can see actually you're gonna see the previous year, you can see we can make a huge improvement compared to the previous the techniques. And so in this case, when we have some pre-trained model, obviously you make another major improvement. This is not the best result. In SML this year, we increased this a little bit by a few percent, quite a few percent, because there's still lots of things you can be done to make this model much better. So based on this idea of TIL plus OOD detection algorithm, if we put this in together, then you can prove CIL becomes learnable. It's learnable. Okay. And the SML this year, we proved this guy is learnable. Okay, it's learnable. So what is the requirement for this guy to be learnable? And the OOD detection must be learnable, right? If the OOD detection is not learnable, and now we have a problem. But fortunately, last year, somebody published an article in Europe, published something which says this out of distribution is learnable. Okay. So when I saw this paper, I said, we can prove our stuff is learnable too. It's learnable too. That becomes pretty obvious. Then you just basically have to work on it. Okay, just work on it. All right. And if you think every of this OOD model is learnable, I mean, obviously you have a collection of them, it should be learnable too. It should be learnable too. Okay. Any questions so far? Yeah.
You said OOD is learnable or CI is learnable. I'm expecting that they're learnable under certain conditions.
Yes, obvious. Yes, yes. And pretty much the same condition as we require for continued learning as well. Yeah. Yes. So now let's come to this open world learning. Okay, open world learning. So we really got this OOD detection and this continued learning somehow connected. Okay, everything I used in solving this CIL problem. So continued learning, this is we want to go a bit further, and we want to do this open world continued learning. Okay, open world continued. So in terms of learning itself, we're not talking about labeling data, all this kind of stuff, how to discover new tasks, all those things. It's essentially a combination of those two guys. Okay, So you have to detect the novel objects, anything you see which is unexpected, and I've seen it before, and then you try to incrementally learn this guy. Okay, so if we are talking about this supervised learning, obviously the data has to be labeled. So later on, we're going to talk about how do we get this thing done naturally without paying anybody money to do it. So if you think this is the case, then obviously the theoretical result we have presented before is applicable here too, right? It's pretty awesome. Because this part essentially is the continued learning. The second part is the continued. I mean, obviously the first part is just OOD detection. And then we got everything connected. However, I want to say is in real life, we also want to go a bit further, which basically means we want to discover new tasks, and at the same time, we want the system to sort of acquire labeled training data by itself. Okay, labeled training data by itself. Yeah. So that's the thing we call SOLA, and which is this guy was adaptation. So when you see something unexpected, okay, you need to adapt to that situation. And in the process, you have to learn the new thing as well. So this, of course, we are talking about getting training data, and also try to do everything by the agent itself. So I just give you an example, which is my personal experience. I consulted with a self-driving car company for about 1 year, and once we basically took the car for a test drive, and it goes outside test drive, and when we sort of when the car comes to intersection, and the guy just stopped, just refused to move. We look at the front and the right and left, nothing, okay, nothing. Everything is clear. Obviously, we're not in the busy street, but somewhere which is pretty quiet. There's no, at that particular moment, there was no traffic anywhere, no traffic anywhere. So the guy just refused to move. And so the human driver has to take over and then go to the lab. We go to study what's going on, okay, what's going on. Now what we found was one of the sensors detect a small pebble in front. Okay, I just refuse to move. If at this moment there's a dialogue system or something like that to ask the humans what to do, right? What to do. Then the human obviously can tell, just go ahead, right? Just go ahead, and it's completely safe. Okay. You can see in this process, you can collect training data, and then you also get the label. You also get the label. And a few days ago, I see a video clip and in San Francisco, and one of the policemen would say, ask the car, go this way, go this way. The self-driving car just go around this taxi driver, no, go around the policeman. The passenger, there's no driver, no person driver. The passenger was inside. I can't do anything. And so in this case, if there's system in the system, if it's a dialogue system or something, right? You can just tell this passenger can tell the car turn right. I mean, the policeman asks you to turn right, not go around of this guy, go around the policeman. I mean, lots of interesting situations like that. So you can see we have this open world. There are lots of things we need to handle. So we need to have communication with people, basically interaction, all the things. And then these people will give you free labels. You don't have to pay for it. Okay, you don't have to pay for it. All right. And then obviously in chatbot, it's the same kind of situation. I mean, sometimes when you talk to the guy doesn't understand what you're talking about. And can you have an interaction with the chatbot, or the chatbot have an interaction with the human, and then learn what the guy is talking about. Yeah. So that's basically the solar framework. And we want the system to be self-motivated, self-supervised, and become autonomous and adaptive to the real situation. So I need to move a bit fast. So what do we mean by that is essentially we try to add these three orange lines, actually mainly there's top two. And this was the previous sort of situation where we have to do continual learning. But in the process of application, we want the system to discover new tasks by itself. Okay, so this can be done by auto-distribution detection. Okay, auto-distribution detection, and at the same time try to acquire labeled data by the system itself as well. System itself, and then we create a new task, and we got the data. Sorry, we have a task, and then we got the data, and then we can learn this new objects. For example, you see something running around on the street, and if you think about the self-driving car, and can you learn that thing? You can learn that thing. Of course, at the same time, you want to learn whether it's safe or not. Safe or not. So let's have a concrete example of this situation. So let's say we have a greeting bot in the hotel lobby, and there's a robot which is roaming around, basically have a greeting of the guests, or have some small talk with the guest. So for example, the bot sees the existing guest. They say, "Hello, John, how are you today?" All right, basically they'll say, "I know you, and how are you today?" And so this is the normal situation. But what happens if a new guest comes in, and then this new guest has to be recognized by this bot to be new, So you can see this is the auto-distribution detection. At the same time, you create a new task. You have to learn this person. And then the bot basically will have to adapt, right? You have to react. You can't say, I see something, okay, new guest, and then I don't do anything. I just go around. I don't care about it. Okay. So then you say, welcome to our hotel. What's your name, sir? Okay, what's your name, sir? So then you get this class label, right? You get a class label. The guy said, David. Okay, my name is David. And then how do you learn to recognize David? Easy, right? You can take pictures of this David. If you think one profile is not good enough, you can move around. Then you can sort of take pictures to learn to recognize David. So next time when David shows up, then you say, how are you, David, right? And so you can see this process is completely automated, and there's no engineering involvement. You get a class label, you get a training data, and then you learn to recognize David. That's that continual learning. That's what we do for the current continual learning the paradigm. However, the hotel is actually not that simple. Okay, not that simple. All right. How do you know that person is a guest? Right? It may not be a guest. It could be an animal running around. It could be just a piece of furniture, although you've never seen it before. And so we need to go further. We need to go further. That's what we call the characterization. You want to characterize this new object. With the characterization, you can respond because you must respond. Okay, you must respond. With the characterization, you know roughly how to respond. You've never seen this guy before. Okay, so obviously you don't really know how to respond. But with the characterization, you should have some idea how to respond. Okay, so for example, this object looks like animal. Maybe just report to the hotel employee to say, you know, some animal is running around. And then if it's hotel guest, if it's a luggage or something, you can say, welcome to our hotel, and what's your name, sir? So I must say thanks to the DARPA CIL project, and this is the big program with about 100 participants. So that's 2 or 3 years of discussion. So I'm using sort of converged idea. So this will be autonomous system in the open world supposed to be working. Of course, the project itself was not able to build any realistic system, but at least come up with some kind of framework, to do this, And we put in this paper, which is published in the AAAI or AI magazine, probably AI magazine just recently. So what do we mean by characterization? What do we mean by characterization? It's basically try to say, you know, this thing looks like something, you know, then if, let's say this thing looks like a dog. So then you can react like the way you might react to a dog, right? That's what a human do as well, right? You can see it, oh, yeah, it looks like, then probably you'll be scared or whatever, you run away. If something is so small, never mind, let's just go and approach this thing, just go around. So there are 2 things we identified to be important. The first one is similarity. So if this is similar to something, then we might react similar way as we react to that particular animal we know before. Another one is the attributes. Can you identify important attributes of this animal? For example, when we're talking about self-driving car, you might want to, if there's something on the road, you might want to, if this guy is moving or not, right? Is it moving, what kind of speed is moving and what direction is moving, right? Is moving across the road, and I mean, probably want to wait for a while. If the guy still stays there without moving, then you probably have to go around. So with any characterization, we have a response, okay? So in the process, of course, we also do continual learning. We get training data, we got all the things, and then we want to do continual learning. So in the process, since this process is completely uncertain, and this is completely uncertain, we don't know anything about this animal, and we need to do risk assessment. So which basically means we have to go very carefully. Go very carefully. For each decision carries some risk, and then we got to be careful with that. Okay. So finally, we have this more complicated diagram, and which is don't worry about this part. Just look at this part. So when the system detects something novel, which is out of distribution detection, and we want to know, first thing is the decision whether this is relevant or not relevant to our performance task. For example, you talk about a self-driving car, then obviously driving is our performance task. And if you see something unexpected in the shop, somebody is fighting in the shop, I mean, it doesn't really matter, we don't really care. If something is in the middle of the road, we are basically have to care. So that means it's relevant. So we have to then we start to characterize this thing. And then at the same time, we have to assess the risk, and then we have to adapt. And in the process, of course, we have to, in many cases, we have to interact with humans. So for example, in self-driving car, it could be interacting with the passenger or interacting with the human driver, although the human driver is probably not driving. So this gets very complicated, So in the DARPA project, we're trying to do this and just get stuck with the characterization itself. How do you characterize this? You don't know anything about this guy, which basically means you have to have a lot of knowledge. It's not just something relevant to your task. There's lots of other things. So you have to recognize this looks like an animal. Then obviously you have to have a classifier, which classify different kind of animals. If you want to get the attributes of this whatever this animal, whatever thing, you have to sort of detect the speed and detect the movement, direction. All the things gets quite interesting and complicated. So we want to build any robots goes in the real world, and we will have to do those things. Okay. So here I will just give you a simple example. We did some time ago. How can we implement this kind of framework in a dialogue system? Dialogue system, of course, is slightly simpler because it's not involve any real world objects going around you. This gets very complicated. So we have this prototype implementation, which we call the CML, and which is sort of like Siri and Alexa. Obviously, our system is very simple, and we do natural language matching. So essentially, the system behaves something like I save some sort of natural language commands, okay, and now when the user says something, I just go to do the match. Okay, go to do the match. So this is a very simple idea. And it's just applicable to this API-driven kind of application. For example, you can ask weather, and the API go back to the database to figure out what the weather is today. Okay. So for the developer, you just write a set of commands. Let's say smart home. Okay, switch off the lights. Okay, smart home has this particular command called switch off the lights, and then you just write sort of what's the common way people say it. And then you just store that in database. Knowledge base, and then when the people say power on the lights or switch off the lights, switch on the lights, you basically do the match. Okay, do the match. So how do we learn continuously? Essentially, we try to add more stuff into the saved seeds command. We call it seeds command. Okay, so as you don't understand certain things, and people obviously say something new, and then if you go through interaction with the user and you figure out, oh, this guy means that, and then we can save the new command into the database. Okay, So next time when you match, you'll have no problem. So here's an example. This is smart home application. We have an API, and then a particular action will just switch on lights in a particular location. Okay, particular location. So you can see this the API with the arguments, just the location. And then this is the seed command. It could be just say switch on the lights on in. And this is a variable, essentially represents the argument of this API. And put on the lights and switch off the lights, all these things. Then it's just example. Okay, just example. And so this is basically saved. Okay, this is basically saved. And then what happens? Let's see this example. Say we do have this put on the lights in the X1. In X1, this is just say switch. Put on the lights in a particular location. Okay, So what happens if the user give a command, say power on the lights in the bedroom? Okay. Then you can match. And then this guy should match with this guy. Okay. Then obviously we're not talking about the word-to-word match, but we want to use more sophisticated algorithms to do the match. And then you get bedroom. Okay, bedroom. So in this case, no problem. Okay, no problem. What happens if we have unexpected situation? Okay, so now we go to that process of detecting novelty and the characterization and adaptation. So what do we mean by novelty detection? So in this case, it's very simple. Just say the system does not understand what the user is saying. Okay, what is it? So for example, you just say turn off the lights in the kitchen, but there's no turn off here. Okay, there's no turn off. You just switch off. Okay, switch off. So let's just assume, and the system does not understand this particular command. And so you have to characterize what's the stuff you don't understand. Okay, you have to characterize. So in this case, you basically probably figure out this is not okay, and the main guy is just turned off is something I've never seen it before. I don't understand what it means. Okay, so then this characterization will give you a clue what kind of adaptation you want to make. Okay, what kind of response you want to give to the user. Okay. So in this case, the response could be just say, sorry, I didn't get you. Do you mean switch off the lights in the kitchen or switch on the light in the kitchen? So you want to give the answer which is almost correct, probably correct first, right? First. So if you don't do this characterization, okay, if you don't do this characterization, then you probably just say, okay, and I just list out all the stuff I can do, and then you choose, and that's not good. Okay, that's not good because people are going to give you bad reviews. Say your system is actually quite junk. Okay, junk. So in this case, and the user probably just pick up option one to say, it means the first option. Now we learn something, right? And we now knows turn off the lights, and it's the same as switch off the lights. And then we can just add another sentence to say switch off the lights in this particular location, X1. And so in the future, you will not have problems. You will not have problems, all right? So what do we mean by risk? How do we consider the risk in this particular situation? And there's two things. The first thing is you don't want to ask people too many questions to get people annoyed. The second thing is the characterization. If your characterization is not so confident, okay, then you better be careful. Don't ask sort of lousy questions. Okay? So, for example, I'm not sure what the guy is talking about at all. So you don't want to list out and all the possible actions you can do and ask the user to choose. That's not good. And that's not good. So one way of doing that, you want to probably have a default action to say, can you say the same thing in another way? Okay, another way, instead of asking people to choose another way. So this is a two-way of dealing with risk. This risk, of course, in this case, risk doesn't really involve somebody's life or whatever thing, but at least you get people sort of at least give you good reviews. So they're saying this system is reasonable. It's not something which is completely junk. Okay, can be junk. I think this is basically main stuff I want to talk about. I want to give people some time to ask questions. And finally, I just want to mention a little bit of something we've been working on. Is the pre-training of language models. Pre-training language models. Just 1 or 2 slides will be done. So when we have a large language model, if you want to apply to your particular application, you probably have your own data saved somewhere, which is very fine-grained data, rather than those data are available on the internet. And then you want to pre-train, you want to continue pre-train on this model, okay, pre-train this model, pre-train this large language model. And how do you do that? And of course, you can just say, let's just keep going. Let's keep going, I don't really care. But in continual learning, you can't do this. You can't do this. The reason is, although the language model, when the large language model is really large, you're probably not going to change much of this model. But as you go continually learning more and more, you are going to change the language model. You're going to change the language model, okay? So then the objective here is we want to preserve the knowledge, the essential, very important knowledge in the language model. And at the same time, we want to learn more stuff, okay? And so when you just adapt to one single domain, then you probably don't have to worry about it. But if you want to adapt continuously with lots of new domains, then you have to worry about it, because the first guy changed a little bit of language model. Then the second guy sees the changed one. Then everybody sees the changed ones. Then things get corrupted. So the challenge, of course, is how to figure out what is important in this large language model. What are the things which is very important? So we figure out some way to do that, and then we try to mask those things. Soft mask basically means when you're grading backward flows to that important places, reduce the gradient, or just completely block it, reduce the gradient. So those other places not terribly important, and then we can let it go. So this is some results. Obviously, we'll get reasonably good results if you compare with the things just completely, just keep training, okay. So, sorry, I think this is the one. So this, in summary, we basically show and we believe and the CIL is learnable, okay? But it's learnable in that particular setting. Okay, that particular setting, we have something which can deal with forgetting, and then we use out of distribution detection to do it. Okay, to build each individual task model. Okay, so if we think this is one of the way, I'm not saying this is the only way, but probably there are other ways, then the theory essentially unifies these things together. Okay, pretty much same problem, pretty much the same problem. Okay, the most important problem is out of distribution detection. Is the out of distribution detection. Okay, because we have to consider the past and the future, and also, and we need to consider what is the implication. Implication of this, we have to consider the past, we have to consider the future. So what kind of architecture is suitable for that, and what are the features that we want to learn? So we mentioned about cross entropy. Is the cross entropy the right thing to do? If we want to consider everything we don't know, yeah, we don't know. Okay, and then we talk about this for the AGI, for the sort of artificial general intelligence, and we want the system to be completely self-controlled and self-motivated and self-supervised, and to make it autonomous. And then we try to make a system to discover new tasks and acquire new training data. At the same time, of course, continue to learn and evolve, becomes smarter and smarter. Obviously, you have to thank a lot of people and the students, some collaborators, and over the years, I've sort of fundings. This particular project funding come from various places, and the open world part is mainly funded by DARPA, which completed last year. And there's lots of discussion about this thing, and now they have new ones which is going on now. I think it's not released yet. I think that's it, and thank you very much.
So you talked a little bit about risk assessment. I'm wondering, thought a little bit more about these autonomous agents that are perhaps learning new things. How to make sure they're not doing too crazy environments that may be more adversarial.
Yeah, I mean, that obviously is a very important problem, but the project itself, I mean, in terms of just our project, nothing has been done. Yeah, just basically identify the framework. Everybody sort of agree this is the framework you have to deal with, but how to do it, and nothing. And it's basically stopped here. Anything below, nothing being done. At least in this DARPA project. I think it's very much depends on individual application. Yeah.
So talking sort of about this idea for it would probably, you're saying it would work well for individual applications. Have you ever see this working for something like virtual assistant? You mentioned like Siri and Alexa and beyond, or like the reception example, right, where you have different things a person might want to do. But I think the assumption, it seems to me, that you have all these different classes and everything can be sort of separated into disjoint sets, kind of might be less useful in open-ended environments with a more general agent. Yeah.
Okay, I think theoretically that's no problem, because when we write the paper, the reviewer has the question, say you assume this guy is completely disjoint. But in real life, let's say you do see the dog today, see the dog tomorrow, but they're still the same dog. They're still in the same category. So the category itself, the class itself, are disjoint. So what we mean is basically dog and the sheep, they are nothing sort of in the middle. That's what I was saying. Not means you don't see the dog in the future anymore. It's just the individual class has to be sort of disjoint. The domain of the individual class has to be joined.
Sorry, but in this scenario, if you have like a dog that looks slightly like a sheep, wouldn't that, like, I'm wondering the joint in what sense that the concept of the class are different, but the observations cannot end up arbitrarily close, right? Sometimes.
Yeah, but when you do theory, you make some assumptions. But in real life, that's the situation for human, right? This dog look like a sheep. We have a problem too, right?
And is this the only assumption, or is there other assumptions?
Yes, that's the only assumption. Basically, just assume all the classes are disjoint.
There are no more questions. Let's end.